Prove using algebra that n plus 1 all cubed minus n cubed is odd for all natural numbers. Now you might be tempted to split this into two cases straight away, odd and even, and it will work. It's just going to be quite a lot more effort. What I would advise is first expanding it in terms of n, because this is actually quite a nice binomial expansion. It's actually just the coefficients of Pascal's triangles. You can even just go like this and write them straight down. Okay, that is your classic one for when you have x plus 1 cubed, the coefficients, or in fact, they are the binomial coefficients, even if you had x plus a all cubed. So it's going to become n cubed plus 3n squared plus 3n plus 1 minus n cubed. By all means, expand it as a triple bracket if you prefer. This is simply going to become 3n squared plus 3n plus 1. Now, you might be tempted to put your cases in at this point, and I will talk about that, but here's an even better way of doing it. We can actually factorize 3n out of the first two terms, leaving us this, and then spot that I have n and n plus 1. So 1 of n and n plus 1 must be odd. So the other is even. And that means we have 3n n plus 1 plus 1, which is an even number, plus an odd number, and this will be odd. And that is all we need to do. Proof complete. This is the best method. This is just like so quick. We just expand it out, spot that that first term is even, and we're done. If we don't spot it, don't stress. We can split it into the two cases. This is kind of the standard teaching process, the teaching method for doing this kind of thing. And sometimes it'll be necessary, but if you don't, it just so happens we get it like this. So it's still worth kind of practicing the second case. So case one, let's say that n is even. And so let n equal to p, where p is an integer. I could write that if I wanted. Then I'll get 2p. Sorry, let me write down the whole thing again. I mean, I'm tempted to just substitute 2p into here, and then I can clearly see that I've got an even number here, but I'm kind of actually going back over the argument already made. So let's imagine that I put it instead into the 3n squared, then I'd get 3 times 2p squared plus 3 times 2p plus 1, which will become 12p squared plus 6p plus 1. I can factorize out, well, actually, I'll just factorize out a 2. 6p squared plus 3p plus 1. This is 1 more than a multiple of 2, 1 more than an even number. So is odd. Then the same thing, case 2, n is odd. So this time n is going to be 2p plus 1. Then I'll get 3 times 2p plus 1 squared plus 3 times 2p plus 1 plus 1. This becomes 4p squared plus 4p plus 1 plus 6p plus 3 plus 1. 12p squared plus 12p plus 3 plus 6p plus 3 plus 1. 12p squared plus 18p plus 7. And I can again factorize a 2 out. A little bit more technical this time. I could leave a 7 there and say that's odd, but even better is to factorize, like take a 3 out. So I've got my 6 and then add 1. This is now written in the form of an odd number again. So again, this is one more. And then multiple of 2, so is odd. We've looked at both cases and shown it, so again, proof complete. Right, so hopefully you can take on board both of those methods. The one on the right is a bit more general for when you you don't have this situation. There might be times where you might show something as a multiple of 3 and split it into the 3 different cases. There's lots of different things you can do. But in this case, it works really nicely with odd and even, so that's something to practice for this kind of situation.